Hello, everyone, and welcome back. I'm very excited to be here today. We have some exciting news. Version 1.5 of ADIAT is now available on the Texar website, and wanted to take this opportunity today to share a little bit about some of the new features that are available, including a brand new algorithm. So let's go ahead and start there. So the MRMap algorithm, for folks who aren't familiar, MRMap is an application created by team members of Mountain Rescue England and Wales that gives them situational awareness during deployments. It allows them to see real-time location information about their team members in the field. It also has some really cool drone capabilities. It's basically an end-to-end solution that allows them to plan drone flights, autonomously fly them, and once the drone comes back, analyze the imagery looking for anomalies. And it's that last piece that we were able to collaborate with them on and bring over a version into ADIAT. So very, very thankful that they were willing to work with us on that. David Binks over on that team was the person who we were collaborating with and who I believe worked on a lot of the drone software for them. So thank you very, very much to David and to the entire Mountain Rescue England and Wales team for being willing to collaborate with us and bring their algorithm into ADIAT. So as we start to look at the MRMap algorithm, the first thing we're going to do is actually do a little bit of a revisit on histograms. So we've talked about histograms in the past, especially talking about histogram normalization. Now, MRMap or the MRMap algorithm also relies on histograms, but a different type of histogram. And I didn't want to confuse users, so I'm going to back up a little bit, talk about the histograms that we're talking about for histogram normalization, and then the new variant of histograms that we're talking about for the MRMap algorithm. So going back to histogram normalization, what we use there are called exposure histograms, and this shows us basically the intensity, brightness, luminance, however you want to think of it, of an individual pixel. It doesn't consider color, it's just how intense is that pixel on a scale of 0 to 255. So as an example, we have our image here, and then we can see the exposure histogram where if looking at this, the average intensity is somewhere around 150 on a scale of 0 to 255. What we're looking at for MRMap is a RGB histogram. So this is actually considering the red, green, and blue channels, and basically just looking at the pixel or the distribution across all the pixels of where it falls on those 0 to 255 scales for the three color components, the red, the green, and the blue. So if we look at an RGB histogram, this is what's used for MRMap algorithm, we see we have the three lines representing the red, green, and blue channels, and we see where the average pixel intensities lie, or the frequency of various pixel intensities throughout the same image. Now, where does this fit into MRMap? So MRMap algorithm works by creating a quantized histogram. Now, what is quantization? It's the process of reducing the number of possible values in a data set by grouping similar values into discrete levels. So if we think about the RGB color model, which is this kind of cube here, three-dimensional cube, because we have three variables, red, green, and blue. In a normal set, we have, or in the normal model, we have 256 possible values for red, 256 possible values for green, and 256 possible values for blue. Multiply all those together, that gives us a total of 16,777,212 possible colors. What we're trying to do with quantization is simplify that. We don't want that many kind of buckets of color. So if we think about it, in a standard histogram, we have 16,777,000 colors. Each one of those kind of corresponds to its own bucket. We're saying, hey, how many pixels are there with a red intensity value of 100? Well, there's somewhere right around 100,000. We want to, again, simplify that so that we can do some analysis on those. So instead of giving each individual color or each individual color channel color its own bucket, we're going to say we're going to turn those 16,777,000 colors into just 17,576 buckets. So the buckets are bigger, and each bucket contains multiple different colors now, if that makes sense. Basically, we're trying to create fewer buckets and put more colors into each of those buckets. So now, since we only have 26 buckets, 0 to 25, instead of 0 to 255, our frequencies go way up because we're putting more into each of those buckets, but there are fewer buckets to analyze, if that makes sense. And as we bring all this together, hopefully this will make a little more sense. The other concept we're going to look at specific to MRMaps or the MRMaps algorithm is a different way of grouping anomalous pixels. So in all of our other ADIAT algorithms, we look at immediate neighbors only. So if these blue squares represent pixels that were anomalous, if there was another pixel in any of these green X's, green boxes with an X, that was also anomalous, it would be considered part of the same anomaly. So it has to literally be touching another anomalous pixel for it to be considered part of the same anomaly. And what we have with the MRMap algorithm is a proximity window. So instead of actually touching a neighbor, as is the case here, we have a buffer of sorts and say, hey, if a pixel is within 3 in any direction, in this case of another anomalous pixel, we'll go ahead and consider it part of the same anomaly. So these 4 pixels would all be considered part of the same anomaly, even though only 2 of them are actually touching. Now there's some implications to that because it's a much more aggressive anomaly grouping mechanism. We'll talk about that when we do the actual demo in ADIAT. So what does this look like when we put it all together? So the MRMap algorithm, it simplifies the image colors into manageable number of groups using the quantized histogram. It then identifies which pixels it identifies pixels with colors that are less common than a user specified level. And then it looks for other pixels in close proximity to those pixels to identify anomalies. Our 3 inputs. Image segments, we didn't talk about this directly, but this is a concept we've talked about before on the RX anomaly detector. That's just the ability to slice the image into smaller images to analyze a portion of the image instead of the entire image all at once, especially useful in cases where an image is very busy or varied and the left side of the image is a completely different scene than the right side of the image. We don't want all those pixels compared against each other because they're completely different scenes. The 2 we did talk about, window size, again, that's that proximity. How close does it have to be to another anomalous pixel to be considered part of the same anomaly? And then the threshold. And the threshold is our cutoff for what is the minimum number of pixels in a particular quantized bucket, where if it's less than that number, the bucket is considered to be anomalous. So putting that together, we start by creating our quantized histogram. We go from 16,777,000 colors down to our 17,576 color buckets. We then look at each one of those buckets and say, hey, is the number of pixels that fell into this bucket less than the threshold? If it is, then we consider all of those pixels to be anomalous. And then we can bring it all together and we look for other anomalous pixels in the image and group them together into those anomalies. So that 3-step process, we create the quantized histogram, we evaluate the histogram to see which of the buckets are below the specified threshold, and then we create or find our anomalies within those pixels, or combining those pixels into anomalies so that we can go ahead and identify those as areas of interest. With that background, we're going to jump over into ADIAT and see what this looks like, and we're also going to look at a couple other features there. Over in ADIAT now, I have my input and output folders already selected. Min object area. So as we talked about, the anomaly builder detector is much more aggressive in the MRMap algorithm than some of our other algorithms. So I'm going to set that min object area much larger than I would otherwise to account for that. Now you see here we have a new attribute or parameter called max object area. This was implemented by John O'Keefe from El Dorado SAR in El Dorado County, California. thank you very much, John, for collaborating with us on this. He is the first person to directly contribute code to ADIAT outside of myself, so a milestone in of itself for our open source model and contrib model. So thank you, John, for being a part of the ADIAT journey and contributing this and a couple other features we're going to look at here in a second. So I'm going to leave the max object area off for now. I'm going to leave the rest of these settings as they are. Switch over to the MRMap algorithm, and we have our three parameters. We have image segments. I'm going to leave that at 1. Window size, that's that proximity buffer for how close does an anomalous pixel have to be to another anomalous pixel to be considered part of the same anomaly. And then threshold, which roughly corresponds to the maximum number of pixels in a bucket before it is no longer considered to be anomalous. Now, it's not quite one-to-one. There's some math going on behind the scenes depending on the image size to try to normalize that. But you can think of it that way. It's, hey, how many pixels need to be in this pixel bucket or this quantized bucket before it is no longer considered to be anomalous. So we have our 3 parameters set. We'll go ahead and hit start. And I will go ahead and speed this up for us a little bit. It does take a little while to run, not as long as the RX anomaly detector, but a little longer than some of our other algorithms just because it is not color specific. It is looking at the entirety of the image and identifying its own anomalous colors. All right, just under 80 seconds later, we have processed our 158 images, and you'll see it found areas of interest in almost all of them. So that's going to tell us there's, just by the nature of these algorithms, because this isn't looking for a specific color, much like the RX anomaly detector, we are going to have to deal with a lot more false positives. But it's the give and the take. It's going to find things that aren't necessarily what we're looking for, but it's also not going to miss things like we could potentially if we were looking for a specific color range. So let's go ahead and jump into the results viewer. There's a couple of new features here. We'll talk about those in a second. But first, let's see what it found. So it did in fact find our red shirt here. And as we said, it found some plants that were, in color ranges that weren't in line with the rest of the image. So as we go through the rest of our image, those false positives, yep, they're going to be there. But you know what? It is so quick to move through those and move on to the next one. In fact, with some of the features that were added in version 1.4, we can go ahead and skip those images. You see them getting grayed out down here at the bottom. That means that as we go back and forth going forward, we're just going to bypass those and not have to worry about them any further. So you see how it works. It's finding anomalous objects in the images. Let's see if we can find one of the other shirts here before we go ahead and close out the viewer. Now back to our red shirt. Let's move further along and see what else we can find. Okay, there we found 2 of our blue shirts in the field as well. So as I said, definitely not color specific, just looking for anything anomalous in the image based on how many pixels are in a similar color range. That is it for our look at the MRMaps algorithm. Let's go ahead and look at a couple of other new features that were implemented in version 1.5 as well. So I'm going to switch back to our good old color range algorithm for now, just to get a slightly smaller image set or result set. Go ahead and let that run. Should finish up our 158 images. So again, make sure you set your min object area back down. One more try. All right, now we're finding areas of interest. So as we go into the results viewer, we see a few new things going on here. First, again, a feature implemented by John, the ability to see the XY coordinates for the center of an anomaly just makes life easier if you're trying to find it on the full image. You don't have to scan from the whole image. You can kind of get a sense of where it is in the image and look directly there. As we mentioned in 1.4, we added the ability to hide specific images. That's going to come into play for a couple of our other new features here. So I've gone ahead and hidden 3 of these images. Now we have I've moved the KML generator up to the top here and added a couple of other generators as well. So we've got our map balloon, that's our KML generator. We also have a PDF report generator and a zip bundle generator. So let's start with the PDF generator. Again, implemented by John from Eldorado SAR. Thank you again, John, very much for all of your contributions to version 1.5 of ADIAT. So when I click on that, I'm going to give this a name. What it's going to do is bundle up all the images that have not been hidden here, as well as the algorithm settings and all of the areas of interest, and create a nice PDF report for you to be able to hand off to incident command or whoever it is who needs to be able to see that and decide what to do next based on the findings from the image analysis. So let me go ahead and pull that up. And here is that report. So we start with our title at the top, including the date and time that the report was generated. We have our table of contents, including direct links to the algorithm settings, as well as each of the individual images in the result set. If we scroll down to that algorithm settings section, we have all of those parameters that were used to run the algorithm in case we need to regenerate it later on. And as we go down to the images section, we have the count of the images that were not hidden. We have each individual image name, the location with the coordinate system that you have defined in your user preferences. We have a scaled down version of the image, and then the areas of interest, complete with the thumbnails and the XY coordinates in the image. If you have an image with multiple areas of interest, all of those areas of interest will be listed below that. Again, thank you so much, John, for contributing this to our code base. The other exporter that we added this time is a zip bundler. So as I said, we have the ability to hide images. Again, if we're handing off image sets to somebody else, it just makes it easier so that instead of giving them the whole output folder, which would still include images that have been hidden, we can create a zip bundle, and that will only include the images that have not been hidden. So again, just makes it a little easier to package this up and hand it off to law enforcement or whoever you're handing it off to say, hey, here's the images that we found with areas of interest in them. Last feature that was added with version 1.5 is down here in the status bar, and that is relative altitude. So most of the modern drones, at least the DJI and Autel varieties, include relative altitude in their metadata. Now, when we say relative, it is relative to the takeoff point. So we've gone ahead and included that here. It just makes it easier to get a sense of the scale of things. And if you need to do any sort of ground sampling distance calculation, gives you a reference point to use. Now you see I have it set to feet. That is configurable as well. If we close out our viewer and go over to our menu and preferences, you can go ahead and set the distance unit to either feet or meters. Again, another feature implemented by John. Thank you so much for all of your contributions this go around. And to all of you, thank you for your continued interest in ADIAT. If you have any questions, concerns, by all means, please feel free to reach out and we will address those.